Hi, my name is Rudy Ryan Anna Gilbert and my registration number is 1124100226. So today I will present about introduction of transfer function. The transfer function h omega of a circuit is the frequency dependent ratio of a phasor output y omega, which is an element voltage or current, to a phasor input x omega, source voltage or current. So the formula used to find the h omega is y omega over x omega. Next is Bode plot. Bode plot are semi-log plot of the magnitude in decibel and phase in degrees of a transfer function versus frequency. Combination in transfer function h omega. First is a gain k, second a pole j omega power of -1 or 0 j omega at the origin. Third is a simple pole 1 over 1 plus j omega over p1 for 0, 1 plus j omega over 0 frequencies. Number 4 is a quadratic pole 1 over 1 plus j2 zeta 2 omega over omega n plus j omega over omega n power of 2 or 0, 1 plus j2 zeta 1 omega over omega k plus j omega over omega k power of 2. This table is a Bode plot summary used in control system and signal processing to analyze the frequency response of transfer function. It shows how different basic components, called vectors, of a transfer function affect gains and phase in a Bode plot. First is K, flat horizontal line at 20 log base 10 of K in decibel, meaning it doesn't change with frequency. For phase, constant at 0 degree because it's a pure gain with no frequency effect. Second is j omega power of n, slope with line plus 20 n decibel over decade. It increase as frequency increase. For phase, constant at plus 90 degree n. Phase lead depend on n. Third one is 1 over j omega power of n, slope with line minus 20 n decibel over decade. It decrease as frequency increase. For phase, constant at minus 90 degree n. Phase lag depend on n. Number 4 is 1 plus j omega over 0 frequencies, power of n. For gain, it's flat before omega equal to 0 frequencies. Increase at plus 20 n decibel over decade after omega equal to 0 frequencies. For phase, start at 0 degrees, increase gradually to 90 degree n around the frequencies. Plus is 1 over 1 plus j omega per p power of n. Flat before omega equal to p and decrease at minus 20 n decibel per decade after omega equal to p. For phase, start at 0 degrees, decrease gradually to minus 90 degrees and around the frequencies.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Faizal binti Abdul Al-Hakim and my matrix number is B112410231. I will start my presentation with question C, transfer function. Today, we will analyze and plot the Bode magnitude plot of the following transfer function. Question C. Step 1, we need to convert the transfer function to standard form. This format allows us to analyze the system as a combination of basic Bode plot building blocks. Step 2, we need to identify each component of the transfer function. The numerator s plus 2 is a 0 at s equal to -10, while the denominator consists of a pole at the origin, s equal to 0, and a double pole at s equal to -10. So, we will have 1 0 at omega equals to 2, two poles, one at omega equals to 0, and the other one at omega equals to 10. Step 3, we need to express the frequency domain. This frequency domain can be broken into simpler parts. Positive 40 dB gain for the constant 5, positive 20 dB over decade from the 0 at omega equals to 2, negative 20 dB over decade from the pole at omega equals to 0, negative 20 dB over decade from the pole at omega equals to 10. And step 4, we need to know the breakpoint analysis of the kernel frequencies that occur at omega equals to 2 and omega equals to 10. These are the frequency where the slope of the Bode plot change. The final parts, sketching the plot. To start sketching the plot, we need to start at the low frequency, which is before omega equals to 2. Initial slope, negative 20 dB over decade due to the pole at origin, and start at magnitude 20 log 10 5 equals to 40 dB from the DC gain. And at omega equals to 2, 0 kicks in and the slope becomes 0. At omega equals to 10, put at 10, the slope becomes negative 20 dB over decade.
Hi, Assalamualaikum. My name is Nurul Arif Hakimi bin Nurul Amin. My matrix number is B112410239. Mention about phase plot from transfer function given. So as you guys can see here, this is our given transfer function, and the question asks us to make a phase plot. So this is my phase plot, and then first step we need to determine the Z1 and P1. This is the Z1 over 10 equals to 0.2, 10 multiplied by Z1 equals to 20. So we can see the green line is for Z1 and the red line is for P1. Can look first at the green line. From 0.2 it goes up 45 degree and then stops at 20 and then it goes 90 degree. Why we can 90 degree? Because 2 decibel equals to 0 minus 90. And then the P1 from 1 here it goes down to negative 45 degree and then go negative 90 from 100 here. Okay, and then the final plot is from 0.2 here we go up to 45 degree and then stops at 1 here and then it goes 90 degree from here, yeah, and then negative 45 here, stops at 100 and then it goes back to negative 90 degree. Yeah. So this minus this and then you get 90 degree.
Hi, Assalamualaikum. My name is Nur Sabrina Yudina binti Zulkifli and my metric number is 1124100178. So my part is going to explain how this question 4G is about plot. Okay, so from the graph given, initial slope from omega equals to 0 to omega equals to 10 radians, the magnitude is constant at 20 decibel. This indicates an initial slope of 0 decibel. First corner frequency at omega equal to 10 radian, the slope changed from 0 to positive 20 decibel. This indicates the presence of a simple zero. So for second corner frequency at omega 100 radian, the slope changes from positive 20 decibel to negative 20 decibel. To achieve this change, there must be a changes of negative 40 decibel. This indicates the presence of two simple pole or one double pole. Looking at the calculation, it's treated as two simple pole. Third corner frequency at omega 100 radian, the slope changes from negative 20 decibel to negative 40 decibel. This indicates the presence of another simple pole. So this is calculation for question G. First, we need to find the initial gain, which is K. So 20 log 10K equals to 20 decibel. So we got K is 10. And then first step, we need to simple zero slope, 20 decibel. At omega 10 radian, so 1 plus JW over 10. Second, simple pole slope, negative 20 decibel at omega 100 radian. 1 over 1 plus JW over 100. And for third, simple pole slope, negative 20 decibel at omega 1000 radian. So 1 over 1 plus JW over 1000. So this is how its calculation works step by step. You need to put initial gain and then divide by simple zero slope at omega 10 radian over for second step and third step, which is for omega 100 radian and 1000 radian. So we need to same the denominator. After that, we can calculate till the end and get the answer.
Hi, Assalamualaikum. My name is Nur Syahira Shamini binti Samsamuddin. My matrix number is 112410194. So for the discussion, in this task, we studied different transfer functions to find their Boyd magnitude plot. A transfer function shows how a circuit or system reacts to different input frequency. By writing the transfer function in its standard form, we could find the zeros and pole, which are key point that affect the system's response. We use this point to draw the Boyd plot. The plot helps us to understand how the system behaves as frequency increase. In the Boyd plot, each zero makes the line go up positive decibel per decade and each pole make it down by negative 20 decibel per decade. By looking at how the line change, we can tell how many zeros and poles there are and where they are placed. This method makes it easier to see and understand how the system works without needing to solve complex equations. In conclusion, this project helped us to see how circuit transfer function is closely related to how it behaves at different frequencies shown through the plot. By studying both, we learn how the system can increase, amplify, or reduce weakened signals at certain frequencies. This is important in building things like filters, amplifiers, and control system because it helps engineers know how the system will react. It also shows us how the map behind a system connects to what we can actually see and measure in signal processing. This makes it easier to understand and design better electronic systems.